As you said, my name is Jeff Robertson. I work for Simufact Engineering, and today we'll be talking about Simufact Additive. Just a brief overview, Simufact Engineering. For those of you who have not heard of us before, we've been doing manufacturing finite element analysis simulation for about 20 years, starting in forming and subsequently to welding, and then very recently into metal additive manufacturing, focusing on powder bed fusion processes. All of our simulations are based on the MSc Mark Nonlinear FEA solver. Several pain points in metal additive manufacturing powder bed fusion can be addressed by simulation. First and foremost are distortion and residual stresses. When the parts are built up, the thermal expansion, shrinkage, contraction result in a significant amount of residual stress that can have a number of negative effects, including the parts just being out of tolerance. The parts don't fit when they're removed from the base plate, cut, heat treated. Also can result in collision with the recoater blade, as well as parts failing when put into service. Further, the effects of on quality, including density, homogeneity, and defects or inclusions in the part. Further, the additional challenges of being able to create parts as quickly as possible, repeatably, to improve the productivity of the process. All this really results in several implications, including the need for a expensive iterative trial and error process. That, coupled with the fact that the time and resources associated with this process, the expense of the machines and the materials and the manpower are very expensive, and this is really what's driving the need for simulation. To date, additive manufacturing workflow has been one where it was design the parts for AM, or design the parts for traditional manufacturing and then revise for AM, go through, take those parts to take a best guess at design parameters, build orientation, support structure, removal, cutting, etc., and then build the parts. After building, go ahead and perform an inspection. At the point of inspection, defects would be observed, and then the part would be potentially redesigned through a trial and error iterative process in an effort to achieve a part that's usable in terms of dimensional tolerance, also from the lack of any crack propagation or cracks that might occur during the build process, as well as a number of other potential challenges. Alternatively, if we were going to incorporate additive manufacturing simulation into the workflow, we could take this design process and perform virtual tryouts utilizing simulation in an effort to reduce the number of physical builds that are required. So in this case, we would incorporate simulation after the design of the initial design of the part, but before the first builds. At this point, you'd be able to try out a number of different approaches, whether that be, again, from build orientation, various parameters, as well as changing support structures and heat treatment, cutting, and support removal in an effort to achieve a part that is usable and free from negative effects of the process on the first time that goes through the build. This is significant in that some of these parts can cost many thousands of dollars for a single build, so a trial and error approach is quite undesirable. So from the entire simulation process chain, we've identified a number of steps within this process that can be numerically analyzed. as you can see here, the 4 steps highlighted in red would be the build, heat treat, cutting and support removal, as well as the HIP process. We understand that each of these steps has a significant effect, and they need to be considered fully. They need to each be considered. The order of these steps can be varied and has an effect, as well as the detail or the content of each step. Considering only the build process is only part of the picture. So the way we go about this to effectively simulate the build process is utilizing a calibration approach. So what you can see in the images on the right side is a virtual representation of a physical calibration test specimen. So we would actually go ahead and build up these 3 cantilever beams in the specific machine with a specific powder and parameter set. Go ahead, do the build up, cut, and then upon the cut, you would actually, these parts would rise up. You would measure that deflection or rise, and then each of those 3 numbers would be populated into the software, where the software would actually back calculate the inherent strain values. So in this way, we're able to calibrate the simulation to a specific part, specific machine, specific powder, specific parameter set, capturing all the micro variability that is inherent in each and every machine variation that's out there. This calibration quantifies what we refer to as inherent strains, which are comprised of a number of different strains within the part, within the build process. Further, these strains are orthotropic in nature, meaning that they vary from X, Y, and Z. So once we've calibrated the simulation, the part is virtually built up using consecutive layers. You can see these layers appear quite thick, and they are. In this case, the mesh could be between a ½ millimeter to 1.5 millimeters or 2 millimeters thick. Now, with regard to powder bed fusion, that's quite thick. It could be from 30 to 50 powder layers being applied at any one time for a given element layer. But this is okay because within the inherent strain approach, we're able to capture the phenomenon effectively, even with these relatively thick powder layers, yet still achieving a very good result for residual stress distortion. So bear with me, the animation seems to be not coming through on the WebEx, but what we're trying to achieve here or show here is that even with very large models, we can still achieve fine resolution of details. And when we say fine details, talking something on the order of less than 50 micron resolution. We're able to do this while still achieving a reasonable solve time because the solution is able to be leveraged in a high-performance computing environment. Being able to scale not just on a single core, but across multiple computing nodes using shared memory parallelization and domain decomposition, including message passing, we verify this greater than 256 CPU cores. So after the build is complete, the next step would be to apply heat treatment for stress relief in this hypothetical example. So this stress relief actually can impart additional distortion on the component. To define this, we need to specify the temperature over time of the environment that the part will be subjected to, or the furnace temperature, if you will. Further, we require material properties of elevated temperature, some of which are shown here, and then probably the biggest driver is the creep properties. In this example, you can see on the right-hand side, that the equivalent stress of the part is this Ti 6-4 bearing carrier is very close to UTS, greater than yield before heat treat, and then after it is down to less than 10% of yield. The next step would be the support removal, and again, the animations here would be very helpful, but overall we can evaluate the removal of the support structures not just altogether, but actually the stepwise or directional cutting of the part from the base plate. So in this case, the cutter would actually advance through the part or through the support structures, removing it from the base plate. As you could imagine, that cutting it from left to right or front to back, right to left, would result potentially in a different distortion, because as this part achieves a new equilibrium, as the part is unconstrained incrementally from the support structures and base plate, this part would deflect or distort differently if you're going from left to right versus right to left. Similarly, the support structures can be removed individually if you have many support structures, in a way that we could then optimize the order that the support structures are removed in. The last step in this hypothetical build process that we're going to look at would be the HIP process. Similar to heat treat, it would potentially result in additional distortion and stress relief. In this case, we're prescribing not just temperature over time, but also pressure over time. Some of the similar material properties are required, and then we look at the densification according to the powder law as shown here. So over this hypothetical example, we looked at the relationship of considering various approaches, whether it be changes to the build, changes to the heat treatment, whether it be a different heat treat approach, or changes to the cutting from the base plate and support removal. Similarly, we could also look at things as simple as build orientation or the quantity and location of support structures. But try as we might, even after all of our virtual optimization, very often distortion may still be out of tolerance. So at that point, we really need to look at the potential for compensating the geometry. So in this case, the Simufact has devised an approach where we are able to apply a compensation factor to distorted part shape, and then export a distorted STL for evaluation, or basically being able to iterate on that shape. So starting on the lower left, you can see the initial build geometry where the supports are pretty much uniform in height. After we go through the analysis, depending on how you look at this distortion or how it's constrained, the toe lifts up or the center bows down. To compensate for that, you can see this illustration shows that the nose or the toe of this bracket has descended to where there is less supports near the toe. This is for an illustration to show the point. So the process that we would go through would be to use the other steps that we demonstrated previously to achieve a reasonable or acceptable residual stress state. And then if the distortion is still at an unacceptable level, utilize the distortion compensation to distort the shape prior to build, so that when the build is complete, after not just the build, but build and all the post-processing steps, including heat treat, cutting, support removal, that the part that results is actually within the tolerance and free from an excessive residual stress. In this case, we're going to look just briefly at a case study. And again, we're lacking the animations here. Doesn't seem to be wanting to work very well with the WebEx, but I can certainly share this information with you and on another meeting individually to be able to provide some of these animations. Again, this case, a tie 6-4 bearing carrier, built up layer by layer. In this case, the element size was about 1 millimeter. So going through each of the stages, you can see that after the build stage, on the left side, the residual stress is quite high as the part is fully constrained, but the displacement is relatively low. After cutting from the base plate, the greatest amount of deflection or distortion occurs, as well as a significant relief of residual stress. In the next step of support removal, even greater distortion occurs, and then with a related or associated relaxation of residual stress. Even at this point, though, there is still a fairly significant residual stress state, with many locations on this part having residual stress upwards of yield and close to UTS. So looking a little further, taking the state after support removal and then after a heat treat, we can see that the residual stress state is lowered significantly. Looking to mitigate cracks within the build, we're able to evaluate a number of different drivers, but primarily looking at local residual stress over UTS. So being able to evaluate the localized residual stress as a percentage or as a fraction of the UTS. And this is not necessarily a one-for-one identification of where we're going to have cracks propagate. However, it identifies high-risk areas. So being able to evaluate it and take similar mitigating approaches to the other to the steps we discussed earlier, they're able to identify where and when these parts may result in cracking, and then take steps to avoid that before actually going and doing a physical tryout. So we recently released a version 2 with a number of enhancements. The first being able to position the part within the user interface in 6 degrees of freedom. So being able to move that part around and rotate it, as well as maintaining the offset from the base plate. So if you say, I want to always maintain 2 millimeters off the base plate, then no matter what, it's going to maintain that. Additionally, we're able to specify orthotropic material properties, and this is very helpful in characterizing various support structure types. It's not necessarily required to fully model a lattice or a perforated or a wafer type support, whereas having an understanding of the orthotropic material properties, you can apply those to the various supports and achieve a very good correlation for the stiffness and density of those parts. We're also able to evaluate the process variance without needing to rerun the simulation. So if you wanted to take, for instance, one build for one set of parameters and one build orientation and support structure approach, you'd be able to then take the results of that build and run it through a number of different, let's say, heat treatment, followed by support structure or in cutting, as well as the subsequent heat treat or stress relief. In this way, you avoid having to rerun the build over and over again, and can essentially just shorten the amount of time and calculation CPU time that's required. And last, being able to compare the simulated results with physical test or reference geometries. In this way, we've made it possible to import multiple reference geometries so that the user can compare the distorted value not just to the initial shape, but let's say, for instance, to a blue light scan of a physically tested part. So in this way, you can have a better understanding of how well the simulation is correlating and identify if there's potential areas where we're missing some assumptions or missing some appropriate calibration or detail in the model setup. Also, we can identify if there's certain spots that you need to focus on a little more than others. So looking forward, the outlook for Metal AM, being able to take, in version 3, which is due out later this year, 2017, we're looking at fall to early winter time frame, being able to take a mesoscale approach in which we would have a coupled thermomechanical solution. Also having an automatic or semi-automated optimization of build orientation, support placement, and support structure type. Further, being able to simulate the actual unclamping of the base plate from the machine as it results in a relaxation. And then chaining with a performance FEA. So we can currently chain with MSC, MARC, and Nastran, but being able to have a seamless chaining with an Abacus or an ANSYS is very desirable. It can be done currently, but requires a little bit of scripting, not quite seamless. We would look to be able to have this as a seamless capability. Beyond that, further optimization, automated optimization, and then being able to really capture the entire AM process all the way from the virtual design through the virtual testing to include that performance FEA as well as fatigue analysis. Doing that in one seamless environment. So as a conclusion, the approach we've taken with Simufact Additive enables us to have a very fast and accurate prediction of distortion and residual stress. We do this by utilizing calibration approach. This really enables us to capture the micro variables that are inherent in the metal AM process, and being able to model not just the build but also the cutting, heat treatment, hip support removal really enables us to understand the part all the way from the very beginning to the very end of the process when it is ready to be put in use. Looking forward again, version 3, looking at fall of 2017.